forwards using all my breath.
Good morning, good afternoon, good evening, whatever the case may be. We are back and better than ever, and I am indeed melting with the calculus. It continues to be awesome. Now, recall, the whole point of this unit of instruction is for us to be able to sketch the curves or sketch the graphs of functions without using a graphing calculator, with using calculus. And the next step in that process is being able to tell the shape of the curve and where the shape changes. And those where the shape changes are called points of inflection, and we will get to that. So that's why this is inflections and shape. Okay. When a curve or part of a curve has shape, there's really two choices here. We say that the shape is concave downwards when it looks like this, like Mr. Green here, when it's opening downwards. And we say that it is concave upwards or concave up when it is opening upwards, when it looks like red. But sometimes it's not so obvious on the curve. These are pretty good. Like I think you can see from here to here, it is concave down. Let me draw that on there. Okay, so from here, let me just write over that, around to here, the curve is concave up. It looks somewhat like this. Not perfectly, but I think you can agree that it's opening downwards. And then the shape changes to, did I say concave up? This is concave down. I am so sorry. Concave down right here. It's opening downwards. And then from here it changes and it becomes concave up. It is opening upwards. And the point where that change occurs is called the point of inflection. And of course, instead of going from concave down to concave up, we could have a curve that goes from concave up to concave down. And that too changes at a particular point called the point of inflection. Here we have another type of curve where we have concave up. We hit the point of inflection and it changes to concave down. And the only difference is this curve is continually decreasing, while this curve goes from increasing to decreasing. Another way that we could have a point of inflection similar to this one is if our function was continually increasing and it looked like that, right? Something like that, and we had a point of inflection, so we have concave up to concave down, yet our function is continually increasing. Okay, so we're going to go to the graphing calculator and take a look at this graphically. Now, if you need to take a second and pause, this is a whole bunch of graphs going on here, a bunch of different things. Maybe you need to get your concentration cap on, but you really need to focus here, because if you can follow this, you're in really, really good shape. Okay, so here we go. Let us consider the function x cubed plus 2x squared minus 3x, and that function is in blue and is graphed in blue. I took its derivative and it is in red. So the derivative of f is, or f prime is 3x squared plus 4x minus 3. That's the first derivative. And then the second derivative is in green. It is 6x plus 4. And their graphs correspond to the colors that I have here. Okay. Now let's look at the original function f. Okay. Ignore all the other graphs. Just look at the graph in blue. And I think we can clearly see that from here along to here, this graph is concave down. Then we have a point of inflection right here, and the graph changes to concave up. Okay, now our goal here is to identify, or how do we identify, where does that change place? Where is that point of inflection? So to start, I just want you to take a look up here at the value of the first derivative. Right now the value is 15 rounded to the nearest whole number. And it's going to change as I drag the slope of the tangent to the function, to the curve, because that's the derivative, remember? And let's see what's happening. Well, it went from 15 to 13 pretty quickly, to 12, to 11, 10, 9, 8, 7. I can't even keep up. 6, 5, 4. Let's see what happened. 2, 1, 0, -1, -2. What is happening to the derivative? Well, the derivative is becoming less and less and less. It went from positive down to negative. It's still getting less. And now we are approaching that point of inflection. And at that point of inflection, it is equal to -4 1/3. The derivative now, the derivative of the function. Now, if I start moving it again, watch what happens to the derivative. -4, -3, -2. Oop, I skipped it real quick. -1, 0, 1, 2. Well, what's happening now as I continue to the right? Well, the derivative is increasing. It's getting bigger and bigger and bigger. It's getting larger and greater and greater. Let's do that again. So along here, the derivative is getting smaller and smaller and smaller. But once I hit that point of inflection, the derivative starts becoming bigger and bigger and bigger. Well, where's that happening? Well, when the graph of the function is concave down, the first derivative is getting smaller and smaller and smaller. But once it starts to become concave up, it starts to get bigger and bigger and bigger and bigger. It is increasing. Okay? So hopefully you got that all straightened out. Okay, so I'm going to leave it right at the point of inflection there. Okay, and let's look a little further. I want you to ignore the first derivative here for a second, and let's take a look at the second derivative. Okay, the second derivative, okay, is the green. It's the line. It's the green line there. And notice right here, the graph is below the x-axis, which means its value is negative. And right here, and to the right of this point, it's above the x-axis, or it is positive. Okay, so as I drag this, look at my dotted lines in pink. Once I hit that point of inflection, the second derivative changes from being negative to being positive. Let's do that again. The second derivative, the curve is concave down, and the second derivative is negative, it's negative, it's negative, it's negative, it's negative, it's negative, and then when the curve becomes concave up, the second derivative is positive, positive, positive. One more time. Concave down, second derivative is negative if you're looking at the graph below the x-axis, and concave up, the second derivative is positive, positive, positive. Okay? Well, why is that? Why is that? What is the second derivative? The second derivative is the derivative of the first derivative, right? And that tells me when that function is increasing or decreasing. And if it's decreasing, the second derivative is going to be negative. So if you look down below, you can see that the second derivative is always negative, while the first derivative is decreasing. And then once it stops decreasing, once it's equal to 0, it begins to increase. And if a function is increasing, its derivative is positive. So the first derivative is increasing, and the second derivative is positive. Okay? So, what have we learned? And if you need to go back, go ahead and go back. What we have learned is that when, ready, the second derivative is less than or equal to 0, then f is concave down. When the second derivative is negative, the function is concave down, or the shape of the function is concave down. And when the second derivative is greater than or equal to 0, then f is concave up. It is concave up. Okay? Looky here. Concave down. Second derivative is negative. Concave up, second derivative is positive. Above the x-axis, positive. Below the x-axis, negative. Okay? And here's a nice little summary of it as well, sort of the same thing that I was doing. I put it on here, it's in your book. Maybe you can read through this. It's really the same thing, but I just wanted to do it with a real graph and show you these things. And let's get rid of this. And here's the upshot. If a curve is concave downwards on an interval S, then the second derivative is negative on that interval. And if a curve is concave up on an interval, then the second derivative is positive on that same interval. Okay? All right, I am going to stop there and just to give you a little bit of a break, and then I'm going to give you one example that will be real quick. I just don't want to do it all in one video. So we will see you next time.